The force between charged particles, in one sense, is just like every other force you've ever seen. It's just one more thing that goes on the left side of Newton's second law, where we look at the sum of the forces when we want to see how a mass moves. If we have several charges present, you can find the force on any single charge by adding the vector forces between charges. So this is just like what you would have done last semester. All you're doing to find the net force on, for example, charge 3 is you have to find the Coulomb force between 1 and 3, between 2 and 3, and between 4 and 3. Those are three vector forces, and you have to add them as vectors, and you'll have the answer. So this is an example of a problem that's not necessarily very fun or interesting, but it's in pretty much every physics book because it shows you how to use Coulomb's law. So we're going to do this, and to do it, first we look at the distance between charges 1 and 3. That's just the side length here, 0.13 meters. Coulomb's law says we need to do K, first charge, next charge, divided by the square of the distance between them. So we have 25 nanocoulombs, negative 60 nanocoulombs. We do all this math, and we get this very small force. Again, we wouldn't expect much, of about 8 times 10 to the negative 4 newtons. This is along the line joining the charges, and in this case is attractive, so this is upward in the y direction for charge 3. What about between charges 2 and 3? Now the distance is larger by the factor of square root of 2, right, from the Pythagorean theorem. This is d, this is d, this must be square root of 2d. So we put in the charges here, 45 nanocoulombs and negative 60 nanocoulombs. We put in the distance, square it. Now we get about 7.2 times 10 to the negative 4 newtons. This is attractive, so this means it's pulling in that direction. Because the angle here, because this is a perfect square, this direction is 45 degrees up from the horizontal or 45 degrees down from the vertical, however you want to think of it. So what that means is it has both a positive x and positive y component, and we get it the way we've always done with vectors. We take this times the cosine of 45 and the sine of 45, which turn out to be the same. So we get an x piece of about 5 times 10 to the negative 4 newtons to the right, and a y piece of about 5 times 10 to the negative 4 newtons up. Last pair is here. These two are negative. The distance between them is just 0.13 meters, and they have to repel each other. So we know Q3 is going to get pushed directly to the left by this. We put in our numbers, negative 10, negative 60. We get a positive force directly to the left. So to add up our net forces, we take the 2 that we have in the x direction and get this. The 2 that we have in the y direction and get this. And our net force is about 1.32 times 10 to the negative 3 newtons. The direction, 81.8 degrees above the horizontal, so north of east, if you want to think of it that way. We can also write this, instead of in x and y components, we can write it like this, magnitude and direction. And it turns out that it doesn't matter how many of these charges we have. It would be more painful to do it, but it wouldn't be any new physics if we added 500 other charges spread all over here at different places. We'd just keep doing the same thing. We would do Coulomb's law, which is K, charge we care about, and then each other charge divided by the square of the distance to it from the charge we care about in the direction connecting them. And we can add up the force from as many charges as we want this way.